Okay, so today we are going to continue with the topic of networks on chip. As I mentioned last time, the overall flow of the lecture as well as the majority of the figures over here are courtesy of Professor Anand Raghunathan at Purdue University. What we are going to do today is go into each of these different characteristics and the metrics that we had mentioned last time, which are in some way representative or some way that you can use in order to measure or understand the different kinds of problems that arise when using networks on chip. Okay. So, the first one which we briefly looked at last time was with regard to topology. By topology, we just mean how the different nodes in the network are laid out and connected to each other. Okay, so this is literally the physical or at least the logical connectivity between the different nodes, right. What that means is that the sizes of the nodes or the lengths of the lines that are used in order to draw these links between them may not be exactly coinciding with what happens on the actual silicon system, but these are the actual connections that exist, right. So, for example, over here we have a two-dimensional mesh. There are 9 nodes. In this case, in general, when I talk about nodes, a node is something that's doing some kind of computation, right, and the links are just some way by which I can get data from one node to another. In practice, what will happen is the nodes might be of different types of capabilities. One might be a processor, another one might be an FFT block which is highly specialized, another one might be an FIR filter, another one might be matrix multiplication, right. But we do not care, all that we care is each node is capable of doing computation and we need to be able to transfer data from one node to another. The torus is an extension of the 2D mesh that makes it easier to communicate from one end to the other logically, right, but physically, as we can see, it means that you need long wires which might lead to other kinds of problems. A 3-dimensional hypercube is in some ways better because it provides additional connections between nodes, but once again, how do you actually realize this on physical silicon is a different question, right. Another way of looking at the topologies could be like this. One common topology is when you have a large number of computational elements just connected together in a ring, right. The octagon is one which tries to provide sort of shortcut connections between things that are otherwise far apart and therefore reduce the maximum distance that a packet might that data might need to flow. Okay. And a crossbar is sort of the best case where every node is directly connected to every other node, which means that the latency required for communicating data from one node to another is minimum, but on the other hand, the sheer number of links that you now need to lay out in hardware on silicon will probably make this impractical except for very specific small cases. Okay. So, this much we saw last time. Let us go a bit further and understand what are some metrics that we might use in order to actually quantify what the usefulness of a particular topology is. So, in particular, there are a few different terms that come up. One is called the bisection bandwidth. There are other things called the node degree and the node diameter, which we will go into in a little bit more detail now. So, before understanding that, we need to sort of look at bus structures and understand what we mean when we are talking about bottlenecks. Okay. So, this is the case of a regular shared bus, the original, before we started off with a network on chip, right. And as you can see over here, the blue curve, the blue line, highlighted line shown in the upper part of the figure essentially shows you the best case latency. You can think of it as best bandwidth or best latency, because primarily what we are saying is if I want to transfer X amount of data, how quickly can I get it from node 2 to node 6 in this case, or the other way around. Okay. Now, why I am calling this the best case is the entire bus bandwidth is available to me. So, node 2 can at every clock cycle be transferring data and all of it will be being received by node 6. The problem is what happens when multiple communication channels are required at the same time, right. We did discuss one possibility of having a so called shared bus or a split bus where, for example, if 1 was talking to 2 and 3 was talking to 4, they might potentially be able to talk without interfering with each other. But right now if you have communications of this sort, 1 is talking to 5, 2 to 6, 3 to 7 and 4 to 8, this part over here becomes a bottleneck. Right? And you can see that if that link is capable of carrying, let us say, 1 million packets per second, then depending on the priority, the sort of best case, sort of fairest scenario is that 1, 2, 3 and 4 each receive 250 kilo packets per second throughput on that, right, which means that at any given point in time the latency effectively of transferring X amount of data has gone up by a factor of 4. Okay. A crossbar is in some ways better in the sense that what is happening inside this block over here is that it actually allows us to make any arbitrary connection from the left side to the right side. So 1 can be connected to 5, 2 can be connected to 6, all can happen at the same time. So it gets rid of that problem of the shared bus. The problem now happens when everybody is trying to talk to the same destination, right. So let us say 1, 2, 3 and 4 are all trying to talk to 8, then that becomes an issue even with a crossbar. Is this unrealistic? Possibly, but not too unrealistic, because just think of 8 as the main memory of the system, right. If that was the case, then everybody is very likely to be trying to talk to 8, right, getting data into or out of 8. What about a two-dimensional mesh structure, right? Again, because you have all of these links, in principle 1 to 4, 2 to 5, 6 to 7, well 8 to 9 in this case, all of them can happen at the same time in parallel, right. The bottleneck would come up in this situation where let us say that many of them are trying to talk to 6, right. Now 6 to 7, the 7 to 6 is still open, that has not been hit by a bottleneck, but the other links 5 to 6, 4 to 6 and 8 to 6 are all contending because of the way that the packets were being routed or the way that the data was being routed, right. But what this shows you is, if I look at this alternative, right, which achieves the same purpose, they are all able to talk to 6, right, but they are able to talk through different ports on the interface that 6 has. Okay. So obviously this is at a very high abstract level of description that I am talking about. The underlying assumptions are that 6, whatever communication infrastructure it has multiple ports through which it can receive or transmit data. In this case there are 4 ports, and what we are saying is how can I optimally use all 4 ports, right. And all that this is saying is, in a two-dimensional mesh you may be able to find multiple different ways of getting the data into the same destination, right, which may not have been so easy using either a crossbar or a shared bus kind of approach. Okay. So with all of that in mind, let us sort of just before we get to the actual metrics, slightly closer look at what is a crossbar and why it is called that. It is effectively saying that you have a complete switching matrix over here. So let us say that input two wanted to communicate with output 5, that would essentially be the way that it followed, right. And at the same time 3 could talk to 4, right, that could go on, well, let us use a different color, 3 could talk to 4, okay, and somebody else could talk, let us say 4 could talk to 6, right. All of these things can happen. Essentially what happens is there are switching points, and each switching point can be set to either continue in the direction that the data was coming in or switch it to a different direction, and based on that we can essentially have a so-called crossbar connection. This was pretty much the structure used in the original telephone networks, right. You literally had a crossbar and the telephone operator needed to make the connections between different points in the crossbar to establish a call from a person who is calling to the recipient. Okay. Nowadays of course the way that switching happens is slightly different, but the underlying concept of a crossbar basically allows you to do certain things such as connecting multiple things at the same time. Okay. The cost is obviously high. There are m into n switch locations over here, right, which means that it is very difficult to get this to scale as m and n increase, right. The number of intermediate values that you need to store over here can grow quite dramatically. An alternative that is used to that is something called a multi-stage interconnection network. I have n input ports, m output ports. What will essentially happen is that I could, for example, have a connection that looks something like this. Let us say that I wanted to go from 1 to 5, right. One way of doing it could be that I will go through this, and over here I will switch down to this side. I will then the other way, the switching actually happens over here. Then this one would go through, this could go down here, go through this, and this could go down here. This might be one way by which one could reach 5, right. Similarly, 3 could go to 2 by going through something like this, right. What is effectively happening over here is you have multiple stages, so the total number of switching points that are required may not be m into n. There are ways of designing these intermediate switching blocks, switching stages, such that the overall complexity of this multi-stage network becomes much less than m into n. It allows you, in the best case, to actually get complete m cross n connectivity, right. But there can be situations where you are not able to establish a connection, even though the normal crossbar might have permitted it. Okay. So, you sacrifice some amount of flexibility for a more compact or easier to design implementation. Okay. So, now let us look at some of the node metrics that are used in order to measure the quality of different topologies. One of them is so called node degree, easy to understand. It basically says how many adjacent nodes am I connected to. So, in this case I can see that node 0, for example, is connected to 1 here and 1 here. So, degree is 2 in the ring structure, right. In the octagon I have 3, and in the complete crossbar I will have 7 because I am connected to everybody else, right. So, in some ways, what would you say about node degree? What is desirable? Higher the better, right. So, the higher the node degree the better, because it means that I have more choices in terms of where to send the data next. Okay. But from a hardware point of view, higher may not be good. From a communication point of view, higher is good. One very important term that is used in understanding networks is the so called bisection bandwidth, right. Bisection is essentially saying I need to take the graph corresponding to the connectivity and find a cut set, similar to what we were talking about during pipelining, right. I need to find a cut set, a set of edges that if I remove them will split the graph into two parts, not necessarily equal halves, right, just 2 parts, 2 separate completely disjoint parts, okay, and a minimal set of edges. So, of course, if I remove all the edges, it breaks it into more than 2 parts, that is not particularly meaningful. If I can find a minimal set of edges such that if I remove them, it will break it into 2 parts, or if I add any one of those edges back, it is no longer disjoint, okay, that is a cut set. So, I can identify cut sets. In this case, the cut sets again are obvious. You can see over here that one possible cut set is this vertical line going through between 0 to 7 and 3 to 4, right. What is the bisection bandwidth is essentially the aggregate bandwidth that essentially forms the cut across those lines. Okay. So, what happens over here is, supposing I call this the connection between 0 to 7 as one link bandwidth, 3 to 4 is another link bandwidth. The total bisection bandwidth in this case, that is the total bandwidth of that cut set, is twice the link bandwidth. Okay. Typically what we are interested in is what is the worst case bisection bandwidth for a graph. So, which is that worst cut set which will give us the smallest bandwidth. in the examples that I have given here, they are all identical, right? They are completely symmetric graphs. So, bisection bandwidth for whichever such cut that you take pretty much works out to be the same. In the case of the octagon, it is interesting. What happens is, in order to bisect, I actually need to cut a whole lot of edges. If I add it up, I will find that it is actually 6 times the link bandwidth. Okay. So, this is interesting. Effectively what it is telling you is, the bisection bandwidth in some way is a measure of how many distinct nodes can talk to each other at the same time, right? Because effectively what happens is, the moment 0 is talking to 7, it is as though that link has gone from the network, nobody else can use it. Okay. But if there is some other way by which one can talk to 6, then that is good, one can still continue talking to 6, right, even though 0 and 7 are blocked, I can't go through that route. Okay. The crossbar, once again, as you might expect, gives you the best possible, the bandwidth 16 times the link bandwidth in this case. Another metric is something called the network diameter, which basically tells you, if I have a large network, many nodes, what is the worst case number of hops. Okay. So, a hop in this case comes about, the notion of a hop comes about because we are saying that data is not directly going from source to destination, it is being transmitted through a bunch of intermediate nodes, right. And in this case, the worst case that I could have is that I need to go from somewhere here through all of these links to get to this point. Okay. So, the worst case would basically work out to be 14 hops. I would need to jump through, this is an 8 by 8 mesh, so 7 hops to get to one end, another 7 hops to get to the other vertical end. Okay. 14 hops, no matter which way you look, right, pretty much any way that you try to get through this, the best case scenario is that I need to do 14 hops to get from, in this case, A to B, right. Now, you can come up with variants of that, right, which basically say that I can think of something called a concentrated mesh. A concentrated mesh is essentially saying I will take 4 of these together and essentially maybe give them a common buffer for data, right. So, now what happens? How do I measure the time taken to get from A to B? I essentially need to hop from here to here, here to here, here to here, then here, here and here. Internally I do not care, I only need to worry about the higher level granularity, how do I get data from one end to the other. That happens, for example, if these 4 are able to share a common buffer for the data, for example, right. Obviously, there is a trade off, it now means that 4 of them are going to be fighting for that buffer. So, if those 4 then want to continuously transmit data, once again that might become a bottleneck, but at least the number of hops can be reduced. Okay. There are many variants on this, right. What is happening over here is that you actually have this concept of long links, right. So, a long link will essentially potentially give you the ability to go directly from one end to the other, right, similar to what we had in that octagon case where we provided a shortcut from one end of the graph to the other, right. So, those kind of hops are possible in, or rather in this case it is called a flattened butterfly structure, but in any case you can come up with variants or ideas of your own of how to create those kind of longer hops, right. The problem is, why did we bring about the idea of a network on chip in the first place? We wanted to avoid long wires, right. So, this obviously once again becomes an engineering trade off, right. You want to reduce the number of hops so that the communication is better, but on the other hand, having long wires will require more buffers, it will require repeaters, it will require larger driver transistors, more capacitance to deal with, maybe more power consumption, right. So, as usual in any other problem in design, it is an engineering trade off that you need to come up with. Okay. So, that takes care of the metrics that we are usually interested in to understand the different kinds of network on chip topologies, right. Now, let us look at the implementation aspects. Yeah. Yeah. No. So, for example, you would need to have a long link between the concentrated mesh, that is the group of nodes and the other group of nodes.
So if we have from this corner to the rightmost corner.
Yeah.
So what about the in between cells, like how will
well, you will need to have connections to those also. Yeah. So that's the problem, right? I mean, it essentially says if I want to communicate from here to here, I need another link, and possibly also I might need something. So then it becomes a question: do you really provide links here also? This becomes a question mark. Do I really need to do this or not? Or do I just say that I'll go to the other end and then hop back from there? Okay. So that's my point. I mean, you can make it's not that this is one standard topology. All that it's saying is by introducing the idea of long wires, you could potentially shorten the distances to other things. The trade-off is the long wires will have problems of their own, right? So the design of these things is, like I mentioned last time, it comes down to this problem of so-called small world networks, right? How quickly can I reach my destination? Where are the places where I should provide those shortcuts to get the best impact?